And this part is all about using analytic, trigonometry and exponentiation. The first part was all about functions, the function concept. The second part that we just had a test on was working with algebraic techniques and things to solve and do analytic algebra, finding zeros and learning how to do partial fractions and all these things that are algebraic techniques. Well, another equally important section is going to be, this is our part 3, and this is all about using trigonometry and exponentiation to analyze things. So it's analytic trig and exponentiation. In that exponentiation, we're also including logarithms. It's all about these, if you will, the transcendental functions. We want to be able to analyze them as best that we can. And there's in 2 chapters. Chapter 8 in here is analytic trig, and chapter 9 is analytic exponentials and logarithms. So that's what we'll do each of those. And then after we complete chapter 8 and 9, we'll take our 3rd test. Okay, so let's kind of start introducing this idea of analytic trigonometry. So let's start with that, chapter 8. Analytic trig over here. Well, a lot of times we do analyze trig functions because they're very useful in modeling behavior that is, sinusoidal or circular behavior and stuff like that. So there's a lot of important things in that regard. So if we want to analyze these trig functions, one of the very important aspects of that is the angular relationship between things. So we're going to be looking at how to analyze things such as, some of the things we're going to do is we're going to look at analyzing triangles. Because a lot of times we can take a lot of problems in engineering and triangulate them and kind of get the missing sides. That's how they found, centuries ago, distances to planets and stuff by using the lights and the reflection angles and everything. And they were able to compute those and determine how far things are away. By making measurements on Earth, you can figure out how far something is away using triangular analysis. So we're going to start with that, and we're going to look at some simple techniques and then some more complicated techniques. The other thing we're going to do is, another important thing, is establishing something called the trig identities. The trig identities. Because a lot of times you do analysis and you want to take one trig expression and rewrite it in terms of another trig expression. And we're going to see there's tons of these trig identities. We're not going to cover all of them, but you'll see there's quite a few of them. Because the trig functions, they're interrelated in many different ways. So we'll be looking at those sort of things. And then this is the techniques, and then we're going to be looking at applications of this. So that's what we're going to do in chapter 8. We're going to be analyzing those sort of things as we step forward. Okay, so let's start with the first topic we're going to cover over here, and this is 8.1, and it's something you are probably all familiar with. I know you probably had it in high school since you're in this course, and it's just right triangle trigonometry. And this might be how you were first introduced to a definition of a trig function. Instead of the unit circle, many of you were probably introduced with the right triangle definition. Okay, so what do we have here? Well, we have a right triangle, I'll write like this. At the right angle over here. And this is side A, B, and C. But one fact that we know about right triangles, which will come in handy, we know we have the Pythagorean identity. So that's going to be an important tool that we're going to use. Which says that my C squared is equal to A squared plus B squared. We're going to see this in another alternative form when we start using trig functions as well. So that's an important tool that was going to come into play. Okay, that's a generic right triangle. Well, a lot of times we want to pick a specific angle in this triangle out, and doing that we can then define, if I wanted to, the various trig functions. So let's do that. Come over here. I'm going to rewrite this in a different way. I'm going to put an angle in it, one angle in it. And depending upon which angle you're concerned with, you might have different sort of relationships. Here's my right triangle. Let's say this is my angle here, theta. And instead of doing A, B, and C, what I'm going to do is, this is my angle theta, and I have a side that is adjacent. It means lies along the same reference line. And this would be considered my adjacent side. It has the same reference side, adjacent to the angle theta. This over here would be the opposite side to the angle. So over here, this is the opposite. And we call the length over here the hypotenuse. So instead of A, B, C, we might do adjacent, opposite, and hypotenuse. Those are the names of those three sides. Now, we could define, if we wanted to, my trig functions this way. Let's do that. And then I'll put it on the unit circle, and we'll take a look at the connection over here. Now, we already defined them using the unit circle, but here's an alternative definition to our trig functions. Of the trig functions. And this is probably how you were first introduced to them. This is a simple way of doing it, but we want it to be a little more, analytical and do the unit circle definition. We could define the sine of the angle theta, which today we write as sine of theta, as simply equal to the opposite over the hypotenuse. The length of the opposite side over the length of the hypotenuse. And sometimes you hear that as written out as sine, S for sine, O for opposite, H for hypotenuse. The whole hold of that so, and then you see the cosine is ka and toa. We could also define the cosine as being the adjacent over the hypotenuse. So we could find the cosine of theta. So cosine theta equal to the adjacent over the hypotenuse. And that's cosine is adjacent over the hypotenuse. Everyone talks about so, ka, and then the tangent of theta and by tangent function as equal to the opposite over the adjacent. And this is how sometimes it's defined. But let's take a look. Tangent is the opposite over the adjacent. And then we learned way back when you have chief SOHCAHTOA. And that's how you kind of remember those things. Now, let's equate this back to the unit circle definition. So let's do that so we can kind of see the connection with our original definition and this, to see that they are consistent. They're the same. But we could have started with this as our definition of the trig functions and taken it from there. But instead, we decided to go in from a unit circle approach first. So let's put it all on that unit circle. So I go plug this into my XY coordinate system here. And here's my, now instead of a unit circle, let's do a circle of radius r. So I'm going to do a circle of radius r. Just like we did in chapter 3. We can expand it out beyond the unit circle. So this comes down over here. I want to make it as circular as possible. There's my circle that can extend over this way and looks like that. And this length down here, that's an r value, which is x. And this y would be r2. And if I plug in my right triangle there, there's my triangle over here, and here's my angle theta. Now remember how we defined the x and y coordinates. This is how we defined our trig function. We have had over here the coordinates of that point were just the x coordinate over here was the r cosine theta. Okay, because if this is a distance r over here, because it's a circle of radius r, and my y would be r sine theta. And that's my coordinates at that point, meaning the length of this side over here is my r sine theta. This is the, put it over here, r sine theta. And then over here, this distance here is r cosine theta. Now let's put in what we know. This is what we're calling our adjacent side. There's our opposite side, and there's our hypotenuse. Now let's show that they give you the same definition. So again, let's take a look at that. We have the following. We're just confirming that those definitions are equivalent. Everything one says, the other says the same way. So let's do our, if you will, our definition. So we have the sine. Remember, that's defined as the opposite over the hypotenuse. So this length here is r again. Okay, so let's put that in. So the opposite over here of that angle is r sine theta. That's that opposite length, it's that height, divided by the hypotenuse. And I get the same thing back. Then I could also look at how the cosine is defined. And that's the adjacent over the hypotenuse. Well, the adjacent is r cosine theta, also over r. So notice I get the same thing back. Now, if I wanted to, I could also look at the tangent. And then remember that's your opposite over the adjacent. So that's my r sine over the r cosine, so r sine theta over r cosine theta. The r's cancel out, and I get my sine theta over my cosine theta, and that's one of the relationships that we say, and that is how we define to be our tangent theta. It's just your y coordinate over your x coordinate. That's exactly what we have, my y coordinate over my x coordinate. So it's a consistent definition. Now, why do we need two definitions? Well, why are two helpful? I mean, really, technically, we only need one definition, but why is this other approach going to be helpful? Why isn't everything unit circle approach? And the reason being is sometimes it's easier to use this when this triangle is flipped around. It may not be in an easily accessible way. Let me show you some examples. We just switched the triangle around in several different orientations here. And here's that same triangle, flipped, and there's my angle theta, and you have to identify the opposite and the adjacent, but it's a little bit easier to do here. Here's my angle theta is up here. It's harder to be able to visualize the XY coordinate system and set it up correctly. But it's easier when you see a right triangle, find the theta, and then just for the adjacent and the opposite, and the hypotenuse is obvious. So this approach is going to be easy when you're dealing with triangles that are kind of shifted in many different orientations. And that's why it's kind of beneficial to have this approach. So now, instead of everything having to be a unit circle, we just pick out my angle theta. You can pick out your opposite side, your adjacent side, and your hypotenuse, and then you can work all the problems. You don't have to worry about tying everything back to a XY coordinate system. And that's why it's kind of like coordinate free, so it makes it a little bit easier to solve certain problems. Other problems are easier to solve using the unit circle approach or getting some better understanding, it's better, or even circle radius R approach. But in this case, it's going to be easier to not have to think about the unit circle. So you need to understand both definitions and be confident with both. So we only originally defined unit circle because of what we wanted to do, but that does not place this as at any less of a significance, because this is also a very important, if you will, type of analytical tool that we need to use. Okay, so that being said, let's take a look at how do we analyze a right triangle. So that's kind of the introduction. It shows the connection between the two definitions, two different ways of approaching it, two different ways of defining it. And now let's take a look at how do we do it. So we're dealing, again, this is right triangle trig. And what is going to be our focus? What is the objective? The objective between 8.1 and what we're going to see starting tomorrow in 8.2 is to what we call solve a right triangle. So here's our objective. It is to solve triangle. And what do I mean when I say solve the triangle? Well, very simply, to solve means we find the lengths of all the sides and the measures of all the angles. And that's all it is. To solve means we find the length of all the sides and the measures of all the angles. Now, I like to organize it in this way. So let's take our right triangle. And I'm going to use ABC. Although when we set it up, we're going to use hypotenuse and adjacent. But I'm going to use this because we're going to use this kind of analysis all throughout. So here's our triangle. So to solve that triangle means we want to find all the measures. Let me get rid of the theta for now. So I'm going to find all the lengths of all the sides. So I'm going to find A, its length. I'm going to find the length of B, and I'm going to find the length of C. Now I'm going to associate the angle that's going to be opposite the other side. So over here, this is length A, so this would be capital letter, would be angle A. So over here, this is angle A. So that means I'm going to find the length of that side A, but I also want to find the measure of that angle A. Same thing happens. This is B, it's opposite here, so this is the angle. I use the capital letter to represent an angle. It's kind of standard procedure. You don't have to, but this is one way of doing it. Now in this case, for the right triangle, that's relatively easy because the angle C here is 90 degrees. That's not going to be the case when we look at more, different types of triangles starting tomorrow. But when I look at solving a problem, I list all the lengths of all the sides, the measures of all the angles, and I put in what I know. There's going to be certain facts that we're going to get at the beginning of the problem that is going to allow us to find all the others. And you want to check off and find A, B, C, this angle, oops, 90 degrees, not 9 degrees, talking, writing, and this. That's what it means. So I usually set up a little chart over here, not just for the right triangles, for anyone. And I just try and fill in the missing pieces. Once I know that, then I can, use these geometric arguments to solve some actual, problem over here, some application, and then that stuff becomes meaningful and important. So that's what it means. We're going to be solving a triangle problem, but we're going to start with the right triangle. So let's start very simply with an example of right triangle. And the tools that are at our disposal. So here's the problem. Here's example 1. Now we're going to put it all together. And it simply says, solve the given right triangle. So let me give a picture over here. We have the following. Here's my right angle over here. We're given this angle theta here is 60 degrees. We're given the length of that hypotenuse is 4. And we're not given the measure or the length of this side or the measure of this angle or the length of side B. So this is what we're given. That means we have to fill in the missing pieces. I have to find angle A, length A, and length B. So that's what I have. Okay, so let's start with that. So we have A, B, and C. We have angle A, angle B, and angle C. We start by putting in what we know. Okay, so my length A is unknown, B is unknown, but length C is 4. That's 4 units. Okay, I know the measure of angle B is 60 degrees. I also know that angle C is 90 degrees. This is always true for a right triangle. We're going to extend that later on to non-right triangles, oblique triangles. Okay, notice what you have. I have 3 pieces of information here. If I have 3 pieces of information, I'm going to be able to solve for the other 2. Okay, so what are some of the facts that we have? So this is what we have, the facts at our disposal. One fact is that the sum of the interior angles of any triangle is 180 degrees. The sum of the interior angles of any triangle is 180 degrees. Okay. What else do we have? We also have the Pythagorean identity. Which says that a squared plus b squared is equal to c squared. And then we also have our appropriately defined trig functions. So we have the sine of theta is equal to the opposite over the hypotenuse. We also have the cosine of that angle theta is the adjacent over the hypotenuse. And if we need it, we will later on in some other ones. We have the tangent of theta is the opposite over the adjacent. Okay, so these pieces of information are going to enable us to be able to find all the other missing pieces that we have. Okay, let's start. The first thing I would do is I know I can find angle A by using that. These have to sum up to 180 degrees, so my angle A then is equal to 180 degrees minus 60 degrees minus 90 degrees. So A then is equal to 180 minus 150, or 30 degrees. Okay, so I was able to find that fairly easily. Can't quite use Pythagorean identity because I have two unknowns. But let's see if we can kind of figure out from what we have, can we determine some other things. So let's say, for example, I'd like to find out the measure of, say, side B over here, the length of that side B. Well, what do I have? Let's kind of take the connection over here. I'll leave the triangle there. Let me write it over here. So I want the, opposite angle if I want to do it. It doesn't matter. I could take the, do A, do the sine, or we could do the cosine. Meaning we're going to be using one of these relationships. And that's going to help us to estimate the length of one of those other sides. Let's write it all out. For example, say this is my angle. What do I have? I have the sine of theta, right, is equal to B, the opposite over the hypotenuse. So it's equal to B over 4. That's one relationship I have. I have the cosine of theta is the adjacent over the hypotenuse is equal to A over 4. So that gives me some information. This is my angle theta. But I know what theta is. So in this case, I have the sine of 60 degrees is equal to B over 4. Or the cosine of 60 degrees is equal to A over 4. Well, we also know the measures of, or the values of the sine of 60. So remember, I can go back to my unit circle. So say if I go back to a unit circle, and draw it over here, and let's put that angle here of 60 degrees. There's my angle 60 degrees. Well, again, that's my unit circle. I know the measure of my thing. What do I have over here? Well, the cosine over here is 1/2. That's the cosine of 60 degrees. And the sine is that length there, which is the square root of 3 over 2. So I can continue working this. So I'll leave that. Get rid of that. Do it over here. We have all that. We can always revisit that if we need it. And we will very shortly. So what do we have? So I have the sine of 60 degrees, which I said is the square root of 3 over 2, is equal to B over 4. And I also have the cosine of 60 degrees, which is square root of 3. 1/2, and that's equal to A over 4. Well, notice what I have. In both of these, I can easily solve for both A and B. This will tell me then that B is equal to 2 square root of 3, and A is equal to simply 2. Multiply both sides by 4. So I now have what they are. So I have B is 2 square root of 3, and A is 2. Now, let's say I only solve for, say, one of them. Let's say I only use one of these. I didn't use. So I only found B equal to that. I never ventured looking at the cosine. So I found B is equal to this. I could also use that information along with the Pythagorean theorem to find the other side. So what do I have? I have that A squared plus B squared is equal to C squared. Okay. Say I only have B. So I'm looking for A. So A squared plus B squared. Well, B squared is 2 square roots of 3 quantity squared is equal to C squared, which is 4 squared. So I'm now going to use this Pythagorean theorem to also find the other missing side. Okay, so let's do this out. So A squared plus 4 square root 2, I get 4 square the square root of 3, I get 3. So it's 4 times 3 is equal to 16. So I get A squared plus 12 is equal to 16. Subtracting, I get A squared is equal to 4. A is equal to plus or minus 2. Obviously, negative values are not appropriate for triangles. They're all positive lengths, so A is just positive 2. Get the same answer. So sometimes you may only find one of them, one side, and then use Pythagorean theorem to find the other. Or you could use both of those relationships to determine the other sides. And now I've solved the triangle. I found the length of all the sides and the measures of all the angles. And in this case, I've done it exactly. I've done the whole thing exactly. Now, sometimes you can't do it exactly. You don't have nice angles. So what do? Then we're going to be resorting to our calculators. So here's another example. So that was an exact analysis. But we're not always given the ability to find exact. If we can, that is definitely a major preference. Solve it exactly. But in the real world, when you're in the engineering world, it's not perfect all the time. So here's another example. Solve the triangle. Give it over here. And I'm going to write it like this. A, B, C, angle A, angle B. And they've given us that angle A is 27 degrees and B is equal to 9. Length B is 9. I'm given 3 pieces of information because I know this C is 90 degrees. So let's put it over here. My objective is I want to find all the length of all the sides. And I want to find the measures of all their associated angles. This is given. And then in this problem, they started out by giving us A is 27 degrees, and they gave us B over here is 9. So I now have to find the length of A, the length of C, the hypotenuse, and the measure of angle B. Well, the measure of angle B is easy. Again, the sum of the interior angles of all the triangles have to add up to 180. So B is equal to 180 degrees minus 90 degrees minus 27 degrees. So, and I get B is equal to 63 degrees. Okay, so I found my measure of angle B, 63 degrees. Okay, now I do have the relationships between the sines and the cosines. Let's kind of use that now. I don't have enough information here. Now, if I knew 2 of these, if I knew 2 of those, I could find the third measure by using the Pythagorean theorem, but I don't. I need more information to fill things in, so I go to my definitions. So now this is my angle theta over here. That's where my theta is over here, 27 degrees. So it's flipped around a little bit, unlike the other one. So now I'm looking at the sine of 27 degrees. So that's my it's my opposite over my hypotenuse. So it's measure of angle A, length A, excuse me, over length C. That's what I have. The sine is the opposite over the hypotenuse. Now I also have the cosine of 27 degrees. Well, that's the adjacent B over the hypotenuse. So we have both of them. Yes, Ashley, have a question?
Yeah, how did you find out that that was theta and not on the other side?
Well, because it gave me my angle A. You see, in the beginning of the problem it says A, and when you write it like this, A, this is angle A, angle B, angle C, that's where it flips to. That's why this approach is a little bit easier than using the unit circle, this SOHCAHTOA approach. Because I'm going to be giving, all your triangles are going to look like this. Any given triangle is going to look like this. Angle A, angle B, angle C. Side A, side B, side C. A, B, C. That's the way it's going to be. The opposite of little a is the angle, measure of angle A. The opposite of little b is the capital B, which is the measure of angle B. That's why this one flipped. That's why I showed you all those triangles and different orientations. It's really hard to do it with the unit circle approach in mind, but it's so much easier to use a SOHCAHTOA to solve this. You'll see as you start to practice it a little bit. Now let's put in what we know over here. I know B, so this tells me right away what I'm going to need to focus on over here. So let's take a look at this. So let's plug in, I'll use this color, plug in what we know. B is equal to 9, but C is not 9. Well, what this is going to enable me to do is to solve for C, because what do I have over here? Let's just remove this. I have the cosine of 27 degrees is equal to 9 over C, or C, if I flip these, I multiply by C, is equal to 9 divided by the cosine of 27 degrees. So does that make sense? Not A, but 9. Well, I can now go to my calculator and get an approximation for C. I can use my calculators. This is where you have to be careful and make sure your calculator is set for your degree mode. So this is one of the cases where you have to make sure that you're in the right mode on your calculators. So let's kind of do that. Let's go to a calculator and analyze that. Here's our calculator. Let's turn it on. First thing I would do, let's clear out everything over here, is I go and I look for my mode, and I'm in radian, so that would give me the wrong answer. So I got to come over here and toggle on my degree mode. Okay, so let me quit that, and now I can do the calculation. So that measure of the length of angle C is equal to 9 divided by the cosine of 27 degrees. I don't have an exact representation, but this is 27 degrees, and then I can use and get an approximation. So it's roughly, we'll call it to the nearest tenth, so I get a value of 10.1. And I'll just call it that. So doing that, that's what we have over here. We're going to take a look at this now, go back over here. So it's approximately equal to 10.1 units. All right. Got everything right. Okay, so now we have that. So I now know that my C over here is approximately equal to, and this is where an approximation comes into play, 10.1. Well, now I need to find the measure of angle A. Now I could use this. I could put C over here. So I have two approaches. If I wanted to, I could say from this that A is nothing more than C times the sine of 27 degrees. This is one approach if I wanted to. So C is 10.1 times the sine of 27. So I could go back to my calculator and do that. So here I take my length A is that times, I put times over here, and then put the sine of 27 degrees. And get an estimate for that of 4.6 if I round it to the nearest tenth, approximately 4.6. Or what I could have done is use the Pythagorean theorem. Another alternative is the Pythagorean theorem. Don't have to do that. I could simply say that C squared is equal to A squared plus B squared. Well, C squared is 10.1 squared is A, which I don't know, squared, plus B that I had originally is 9 squared. Squaring 10.1, I'll do that separately. And I get 102.01. So this gives me over here, let's kind of work it over here. 102.01 is equal to A squared plus 9 squared is 81. So moving that over, so I get 21.01 is equal to A squared. Take the square root of both sides, and that'll tell me A. And I'll approximate that as the square root of 21.01. And I get the same answer, roughly 4.583. Same thing will come out, and I'll round it to the nearest tenths place. I get 4.6. So either way, I solved the triangle. I found the measures of all the angles and the lengths of all the sides that are associated with that. Does everyone see that? So that's how you solve the triangle, using the facts of information, the sum of the interior angles, sum to 180 degrees. Pythagorean theorem applies. See someone else maybe. Pythagorean theorem is a little bit there. Well, how do I get C by itself over here? Well, all I'm doing is multiplying by C, and so this is what you should be able. Let me just show you this. This is the basic algebra that you should be coming to the course with. So I'm solving this equation. Cosine 27 degrees is 9 over C. So I multiply both sides by C. C's cancel out. So I get C times the cosine of 27 degrees is equal to 9. And I divide both sides by the cosine of 27 degrees. I'm not really switching. I'm actually doing a calculation here. So cancel that, and I get C is 9 over the cosine of 27 degrees. I multiply by C, divide by the cosine. So that's the basic algebra that you should know. And if you're having problems, practice it. Do a lot of practicing, because you're kind of, at the cusp of not being, if you're kind of bogged down by this, all this other stuff is going to be much more complicated. But that's how we solve the given right triangle. And again, you have a choice, because you have the sine and cosine. You use Pythagorean theorem or not. That's going to be left up to you. But this is where it's a little bit easier to think of, if you will, of the SOHCAHTOA approach as opposed to the unit circle approach. Okay, let me give you one to try and see how it works out. Let me give you one. This is a little bit harder to try. See what's given and what you need to find. Now, in fact, maybe I'll do this one. And then I'll have you try them on the homeworks. Let me do this one because I can see this is like a different type of problem than what you've seen before. It's the same thing, but we're given certain information and it's a little bit harder to find out what's happening here. So let me do this one for you. And that's what we'll end with today. So we have our triangle over here. And this is my A, B, C, angle A, angle B, and there's my angle C. And let's say that they've given us just the length of all the sides. So given A is equal to 5, B is equal to 9, and C is approximately, because we can't do it exactly, it's going to contain some radical, approximately 10.3. What would we like to find? Now we're given the length of all the sides. We'd like to find the measure of angle A and the measure of angle B, because we know that the measure of angle C is already 90 degrees. This is a little bit different. In the previous ones, we were able to find that missing angle right away, and exactly. Here, we can't do that necessarily. So this is right here, this is our angle A. So that's going to be our unknown angle. So let's take this. Let's write down what we know about the sines and the cosine. Now we know that the sine of angle A, so remember, is your opposite over your hypotenuse. So it's A over C. Well, what is A? A is 5, and C is approximately 10.3. So that's known information. We also know for the, we also have the information, if I wanted to, about the sine of angle B, if I wanted to. I have the same thing. I have my sine of angle B, okay, so that is just my opposite over my hypotenuse. That's B over C. But B in this case is equal to 9 over approximately 10.3. I can use either of these. I also have the information about, if I wanted to, the cosine. Let's just show it all here. And then you get to pick and choose. What about the cosine of A? Well, remember the cosine of A is the adjacent over your hypotenuse. And you can kind of see some connections over here. So it's my adjacent, which is B over the hypotenuse. And my cosine of angle B is my adjacent over my hypotenuse. And that's the same thing over here. It's 5 over 10.3. Notice the connection here. Okay, what do we have? Do we have information that we can solve? Well, yes, we do. Let's just write it all down here. Let's just start with this one. Just pick one. I'm just going to pick that one just as easy, and I'm going to explain why. So what we have over here is we now have the sine of angle A. That's we don't know. Remember, that's our unknown. Is equal to, approximately equal to. Why is it approximate? Because this is an approximation. It's approximately equal to 5 over 10.3. Well, can I find the measure of angle A? Yes. Remember what we did. We did inverse trig functions. So what I can do is take the arc sine or the inverse sine of both sides and solve for that. So I have the inverse sine of the sine of A is equal to, do the inverse sine of both sides, inverse sine of 5 over 10.3. This is going to give me the measure of angle A. Sine inverse of 5 over 10.3. And it's, again, it's an approximation over here. Now remember, what is the range of the arc sine? Well, the range of the arc sine, remember, is minus 90 to plus 90. It give me something negative 90 to plus 90. Now, if I'm looking at this triangle, A can't be greater than 90 because C is 90. Now, I could also have used this definition if I wanted to. And you can see we're going to get the same equivalent one. I could use that the cosine of angle A is equal to 9 over 10.3, or A is the inverse cosine of 9 over 10.3. What is the range, if you will, of the arc cosine? 0 to 180 degrees. This is going to be the one that's going to be most convenient arc cosine for triangles, because you're never going to get a negative angle. They're all going to be positive. Everything's in quadrant 1. But we can use either one. Let's just plug them into our calculators and see if we can then get an approximation for that angle. And again, your calculators need to be set for the degree mode. I know my calculator is set for the degree mode. Let me clear this out. And what I'm going to do, let me use we'll start with the sine, the arc sine of 5 over 10.3. So second function, inverse sine of 5 divided by 10.3. It's going to be an approximation, obviously. And this is going to come out in degree measure. So it's roughly 29 degrees. Or, like I say, I could also do the arc cosine of 9 over 10.3. And in the end, you get the same exact answer. It's a little bit off over here because of the approximation. So this might give me 29.1. The other gives me 29.4. That's because that 10.3 is an approximation. Approximating to, it's rounding in the tenths place. So this, we can only keep the accuracy here to the degrees place. So what I would say is that angle A now, we now have an approximation for that, is approximately 29 degrees. If I know this to a tenth, I'm only going to know that to a degree. Now what could I do? Well, I could try and solve B over here, but I don't have to. I don't have to do this complicated stuff. I could just use that the sum of the interior angles of a triangle are 180 degrees. Let's use the easiest approach, and the one that's going to give me the nice consistent result with these angles all summing to 180 degrees. If I do the other way, I may be off a little bit. So angle B over here is 180 degrees minus 90 minus 29 degrees. So that's an approximation. So B is approximately equal to 61 degrees. And that's what I get. So I've solved the triangle. I found the measures of all the angles and the lengths of all the sides. But this one was different because this one just gave me the lengths of all the sides. And then I had to use the arc, the inverse sines and the inverse cosines to get approximations for those other angles. So those are essentially the three different problems that you would see in solving a right triangle. Hopefully you get a sense. You have to practice it. You have to practice it. Put down all the information you know. Everything from, you know, the facts that we have, the sines and the cosines of the various angles, and see which one will lead to a solution more easily for you. Because some people prefer one, some people prefer the other. But you can see you have a slight difference when you're using an approximation over here. That approximation causes changes in these two. Now, if I found out what C is exactly equal to, I could find out the exact value of C if I wanted to. Let's show that, the exact value of C. And if I plugged it in, both of these would give me the same angle, approximation to that angle, you know, same decimal. So what do I have? I have A squared plus B squared is equal to C squared. So I have 25 plus 81 is equal to C squared. So 106. So I have C is equal to the square root of 106. So if I plug that into the calculator, both of them would come out to give me the same answer. But because this was rounded, I lost that level of accuracy. But sometimes you're just given the approximate. So in that case, one to illustrate why you do have to be a little bit careful here in terms of what angle you say. This would give me 29, the other would give me 29 or 29.0 if I tried to round it to the 10th place. The other would give me 29.1 degrees. Be a slight error. So this error would propagate to errors in these. But that would be the exact if we had given it from the beginning.